Thank you for all coming on a Friday morning. Really appreciate it. So I'm Manal. I've been at Netflix for several years now, and for the past 2.5, 3 years, I've been working on streaming and stream processing initiatives. And I've helped define the space and the platform that we currently have at Netflix, and I'm going to be talking about that today. So I'm going to be talking about the amazing work my team and I have been doing in the stream processing space and the platform that we've built. I've organized this talk basically based on 3 different roles and perspectives that I have seen when building out this platform. So if you're a data engineer, you'll get a glimpse of why stream processing and what does such a platform offer. And if you're a data leader, then you'll get an idea of what such a product or vision for such a product looks like. And I'll also cover how we build it and how we operate the whole platform. So if you're a backend engineer developing it, you'll get some glimpse of that as well. So I'll focus on the business insights platform that we're building predominantly on Flink. And I won't be talking about the operational insights. We have a separate system called Atlas and Mantis that we use for that. And I won't be comparing the different stream processing engines or cover streaming concepts. I have a separate talk I gave last year at Strange Loop that covers that aspect of it. So if you want it, you can hit it up later. So why stream processing? Right? At Netflix, we have over 100 million customers, and we want to understand how they're interacting with their service, what they're playing, and we want to give them a really good personalized experience. And these interactions that the users perform on our website and also the systems that are backing it, they generate a ton of events. And we want to understand all this ecosystem and give a really good experience to the users. And so for us, getting low latency business insights analytics enables interesting personalizations that we could do. It also helps us do some innovation in marketing of new shows. And it enables a ton of other things that we can do research-wise. And processing data as it arrives also has its benefit, because now you can spread the workload of processing over time. And if you're processing things like data quality, or you're doing some aggregations, you're doing some enrichment up front, then you don't have to repeat those again when you're processing those events again. So you also avoid redundancy. And as we all know, the sources that we see are producing a lot of events, and they'll continue to do so as we have more and more customers. And these are unbounded data sets, right? And so we need a way to kind of efficiently process this and a way of processing this in real time. And so building such a platform gives us both business wins and technical wins when we build it correctly. So why at all build a platform? Why not just let people write their own stream processing jobs? Because building good stream processing jobs that are accurate and latency sensitive and are productionized, it's not a trivial task. And if you let everybody build, you'll build a lot of boilerplate and a lot of redundancy and a lot of wasted development resources. So I think we want our users to be able to focus on actually working on the business insights and not have to worry a lot about building complex infrastructure and the tooling that goes along with it. So you may ask, what does a stream processing platform offer? So a stream processing platform needs to be able to offer users the ability to trade off between ease of use, flexibility, and capability of the platform so that they can pick the right combination for the solution at hand. They may have a very simple thing to do, like a filtering or a transformation, or they may have real complex windowing or sessionization needs. And based on what they need to do, the platform needs to offer ways of doing it and make it as simple as possible and make complex use cases really possible on the platform. So we kind of take a 4-pronged approach towards this. One is the users can set up stream processing based on just a point-and-click UI, and they can set up rich filtering, projections, and they can route it to different sinks that we support out of the box. The second one is if that's not sufficient, then they can create their own streaming jobs. And we are also looking towards supporting SQL-like DSL, so it makes it even easier for them to create those jobs. And down the line, create interactive capabilities so that they can explore the streams and do quick prototyping before they decide to go one way or the other. So we'll first look at the point-and-click approach of doing this and what the product actually looks like. So at the core of it, we have a ingest pipeline called the Keystone Pipeline that offers this point-and-click functionality. And it forms the backbone of our infrastructure because if you want to have events and real-time events, you need a way to kind of funnel them through your system very reliably, and then you can do some stream processing with it. So this pipeline enables reliable event publishing, collection, and then routing them to different sinks for batch and stream processing. So this is completely serverless to the user. It's an out-of-the-box turnkey solution. It runs 100% in AWS. So I have a quick demo here that shows what we do when a user wants to create a brand new stream on this ingest pipeline. That means they want to start producing events, and they have absolutely zero infrastructure at this point in time. So user comes in and starts creating a new stream. They give it a name, and they provide their email address so we can contact them for interesting things. And they provide a brief description so that it helps their other team members to know why they created that stream for, and other people who are involved. They can pick a region and an environment they want to deploy and plug it in. So here we are creating it in test, and they're saying their estimate is 12 megabytes per second for the stream. And once they do that, they say, create a stream. And then at this point in time, the data is not going to go anywhere yet because they still have to configure where the data needs to land in. So they're going to add different outputs. And here we're going to add a sink for Apache Hive. And they add the table name that it needs to go to. And we have a couple of deployment options to address the low latency and low duplicates scenario. And once they set that up, then the pipeline's kind of set. Now they're adding one more filter because they want one unfiltered stream going to Hive, and they want a filtered stream going to Hive. So now they're setting up another filtered stream. And we have an expat-based DSL. We have our own custom parser kind of that supports this. And the data flowing through usually is JSON. So this allows them to quickly write a filter based on the expat language, and it has logical and arithmetic operators that are available for them to group and create this expression. And once they create the expression, as we can see, the error says that you need to send it somewhere, so let's create an output for it. So we're creating another Hive table because we want the filtered events to go to another, and we want to retain the raw stream so we can do additional analytics downstream. So that's what the user chose to do. And once that's done, the user specifies, again, another deployment model, the same thing as before, and they create the pipeline. So that's all the user had to do. Once they do this, we provision the stream for them, and then the user can start publishing. So in a few minutes after they do that, they get the pipeline provision. So what happened here is they created one pipeline to produce the events into, and they created a fan out of two so that you can have the events routed to two different sinks from the same originating stream. So here we look at the different message formats we support. So Chasqui is our own internal custom binary wrapper so that we can support multiple different formats. And we did this so that internally we can evolve the system without having to do a lot of changes. So that today we support JSON, and what you can see here, simple JSON, is nothing but a flattened version of JSON. And that's there because of legacy reasons of how the pipeline evolved at Netflix. And we're also looking at adding Avro in the future, and that we could easily put it in our wrapper and send it across the wire. So at this point in time, we don't have any explicit schemas. The schemas are implicit based on the JSON structure we have that flows through the system. And the other thing they could do is projection. So here's a quick demo on how they could set up projection for the stream. So let's say they want to add one more fan-out stream from this source stream, and they want to include only the fields that match these criteria. So if you have a JSON blob and if you have fields in there called user ID and clicks, it takes a projection of that, and only that information gets eventually sent to the sink. So we are sending this to Hive Sink as well, and we are only sending a subset of the data that's flowing in. So you have a producer that's producing it one time into a stream, and then you have all these interesting consumers who may want to consume just a portion of it, or a projection of the data set of the payload, or just process the whole raw stream. So all this is just achieved by user coming into our system and with a few clicks to have it all provisioned for them. So here's an example of setting up Elasticsearch Sink. So here we let the user specify an index, how we roll the index, whether it's monthly, daily, or weekly. And they can also specify which field is the one they want to use for indexing and what's the timestamp field. So it gives them flexibility to write to Elasticsearch as one of the sinks. We also allow them to write to a Kafka cluster, which is a supported sink out of the box. And here we allow them to specify a partition key so that you can actually write partition messages into the pipeline. And it follows the same syntax of picking the key name from the JSON blob. So this is an example of another pipeline that was set up. Here, the incoming stream is being sent to 3 different sinks: Elasticsearch, Hive, and Kafka. So what just happened is we created a topic on Kafka, we created 3 stream processing jobs, and then we created a topic on the consuming Kafka cluster. And Hive and Elasticsearch are more dynamic. The Hive automatically creates tables first time it sees an event coming from that topic. So all this got provisioned for the users, and they didn't have to do anything for it. We managed the whole infrastructure. And so we'll quickly go through the event flow. We'll keep seeing this image again and again as we dig through the different layers of the system. So the left-hand side, what you see right now is the producer. The user uses a producer library or a proxy to produce the events into our fronting Kafka cluster. Once it's there, these are, we have quite a few of these clusters, and it gets routed to the right cluster based on capacity that we set up and we do. So user doesn't have to do that either. And then we launch the routing jobs that we had created. So there's one for each sink, if you remember, and the data for each one gets routed to those. And if you see, the first job routed the data to Hive, the second job routes the data to Elasticsearch, and the third one routes to the Kafka. And all these are happening in parallel. They're not waiting for each other. And there's a nice level of isolation here, because let's say your Elasticsearch is down. It doesn't prevent your Hive job or consuming Kafka job to be delayed, or events being delivered to be delayed, because each one is running off of a separate job. So there's built-in isolation. So a user creating a filter, and if the filter is bad, they don't impact another user who may have a different stream coming off of the same source Kafka topic. We don't allow keyed messages into our fronting cluster, and I'll go into the reasons why. That's a really highly available part of our infrastructure, and we want to make sure we get every single event that's thrown at us and we don't lose them. And with keyed topics and with the scale we run at, it becomes very difficult to guarantee that availability. So we do offer that functionality downstream. And in addition to creating this pipeline, the framework automatically generates dashboards for each stream. So in this scenario, it would create 3 different sets of dashboards, one for each stream. And this is just a snippet of what we capture. There are tens of metrics that we capture. Here, it's just showing what the producer is producing and what the router is reading from it, what the message lag is, how many messages were filtered, what were not filtered, are there any failures. So just these 2 graphs gives us everything that we need to know quickly. And this is exposed to our users as well, so they can self-serve themselves to see if there are any issues. And they can always escalate it back to us if there's a problem in the infrastructure, because they don't manage any of this. It's serverless. This is more for an admin use for us, behind the scenes for our on-calls. We create searchable index logs from these jobs automatically, so that if something goes wrong, we can quickly take a look at it. Now, we heavily rely on instrumentation and metrics and dashboards, but there are always cases where when you're using a lot of third-party libraries, there may be some logs that you want to take a look at when something goes wrong. So this is where we use it for. It's more of a complementary than do everything through logs kind of approach. In addition to that, We also expose a link directly to the stream processing jobs UI. So Flink exposes a web UI for the job that's running. So we can actually dig in and look further what's happening into the system. So this is the part of the UI that gives access to all these links. So the dashboards, the UI, we can look at the logs, we can look at the job history deployment and see what happened with different deployments. And so it gives one-place access for on-calls or for administration purposes and operations purposes. So it's fully managed. We manage the capacity planning, the scaling of it, the 24/7 operations for it. We even do garbage collection. We look at streams that have not been used for a month or two, and then we inform the users, and then we just clean them up automatically. So it's truly managed end-to-end. And so for the Keystone pipeline, what we're trying to do ahead is add more support for UDF. So you could go into the UI and plug in your JavaScript code or point to a jar, and we'll run it for you as part of the processing. Do some data hygiene modules, do some data alerting so that you can have custom rules in there to fire. And then also an ability to chain all these components in the UI itself, so you can have complex chaining of filters, projections, UDFs, data hygiene, and then you've built a pipeline based on those components. Schema support and data lineage, and we also do cost attribution so that we can expose this to our users and they're mindful of how much cost they're incurring by provisioning that data stream, so that they can either cut back or they can continue provisioning it. And so this is our approach to scaling up by scaling down, because we've had customers or users actually realize that they're spending a lot, and they've looked at their streams and they've trimmed it down because they had excess data going through it, which was never used. So now we'll jump into looking at the product for the streaming jobs. So when would you need to write one is when the functionality provided by the pipeline is not sufficient. You may want to do something more complex than just the basic projection and filtering. So out of the box, we have support for generating a job out of a template. This is very similar to Maven archetype approach, but this is our custom-built tooling for Gradle because it does a lot more than just that. And so we use this tooling to create a quick job. It automatically commits the code for you in a Git repo that you specify. It even creates a Jenkins build. It creates a build pipeline. And it also creates the configuration so you can run the job locally. You can run the job. So this is the Jenkins job it created. And then you can also run it locally in the IDE. Right now we have support for one IDE, the one that's used most widely. And the users can just load it up and then just debug the job locally in their IDE. Once they are ready to deploy it into one of the supported environments, then they come in and create a configuration. So here they specify what their app name is, again, who the owner is, and then we have support for some of the built-in sources and sinks. So if it's one of the built-in source, like Kafka, then we automatically find the cluster for them, we give the VIP name to them, we automatically configure the job for them. So we put these overrides when they deploy it. So for example, if they give us an image, and these are Docker images that they give us, in test environment, it might be connecting to a different cluster. In prod, it might be connecting to a different one. So they come in here and configure those overrides, and then we apply those overrides as configuration when we launch these jobs on our container runtime. So they get some out-of-the-box support for the sources so that they don't fat finger the name of the cluster or they don't have to go and discover it themselves. We keep the list internally, and we can even search it based on the topics as well. So in addition to that, they can even specify the containers they need, what the sizing of that each of the container is. And then there's an option for adding additional properties. That's just a free flow name value pairs they can use to override anything they specified in their configuration files that are packaged in the bundle or in the jar that they provide us packaged in a Docker container. So it's easy to deploy the same job in a different environment, and we're kind of working on the promotion to make it even easier so that you could just say, promote this test job to prod, and the configuration that needs to be changed, they can change that configuration. They can look at a list of steps that were taken to actually deploy the job, because at times there could be some failures, and this gives them an easy way to look at what happened. In this case, the last step of the job is aborted, so they can look and see actually what went wrong, and they could try redeploying it. And this is useful tooling for us as well to look at any infrastructure failures that we may have had. So again, similar to the routing jobs, the user has access to all the dashboards and the search logs that we provide for them out of the box. So we create a bunch of metrics for them. For example, what consumer offsets they're reading from, are they lagging behind if they're reading from Kafka, what are the JVM DC metrics, what are the container metrics, what are network metrics. So there's a slew of metrics we automatically generate for each job when they get to deploy it. And on top of this, the user can customize this dashboard and add their own metrics, application metrics that they define in their code. And we also make it very easy for them to define metrics in their code. We leverage Netflix's Atlas and Servo libraries, so they can just start creating counters and gauges, and everything will show up here. And not only that, but when we have new updates to our dashboard, they can actually select it to update it automatically. So they won't lose their customizations, but we'll actually update all their dashboard with our new metrics. Let's say we added a new metric and we want it to show up. So that automation's there out of the box. And the job logs also show up just like the router jobs. We index them in Elasticsearch so they can take a look at it. So in addition to providing the tooling for building, developing, and deploying and monitoring, it also becomes important to provide good consulting and documentation, especially when you're building out a platform that's in a green space like stream processing. You have to tell users and teach them how to think streaming first, how to approach the problem from a streaming perspective. And so there's some amount of guidance that's necessary as part of this platform. And also to provide some recipes so it makes it easier for them to build what they're building. So we'll quickly look at what kind of stream processing jobs, these kind of custom jobs that we look at. There are two broad categories of these jobs. One is stateless. What I mean by stateless is there's no state maintained between events. They just process an event, they do something with it, they move on to the next one. They don't maintain anything across those events. The second class of events, the streaming jobs are stateful. That means they retain some kind of state across these events. And these could be like windowing or aggregations or joins. And stateless could be you're just doing some map or filtering or just doing a quick transformation and sending the data back onto a different sink. So it's this part of the architecture that we're going to be talking about. We talked about the Keystone Pipeline, which feeds into the consumer Kafka cluster, and these streaming jobs pick up from there. So for a stateless stream processor, this kind of it looks like where each event's flowing through in. We're doing the processing, and then it goes its merry way out. For the stateful, before I go to that. So stateless has two variations. Unlike the traditional way of thinking about it in stream processing, when we talk about stateless, we are talking about what's happening in the process that's processing the events. Now, you could have external database that you're maintaining to write some data to and look up some data. So for example, you can have some lookup data that you want to look up, right? So that's not really considered the state that's being built into the platform itself when you're processing. So it's important to kind of draw that distinction. So now let's take a look at an example of a stateless job. So we have, again, users interacting on our website. We want to understand that behavior and feed this into our personalization system, and also how we can effectively discover these shows. So this job kind of takes that information and feeds it downstream for additional processing. So at the high level, it kind of looks like this, where the play logs are getting into our Keystone Pipeline, which kind of feeds into the stream processing job. This job calls actually a live service, does some enrichment, and also looks up some live lookup data. And then it creates this new payload and then sends it to Keystone, which sends it to Hive, Elasticsearch, and other things. So what we did here is we're using the Keystone Pipeline as a glue for additional processing that can be done. So this job generated a feed that's interesting to different users, and they can take those feeds and then route it to where they need to. And for stateful stream processing, for example, when you're doing windowing, you need to hold the state across events for the amount of duration of the window. Or if you're doing aggregations across those windows, then you need to do the same thing. So in this scenario, you're actually building up state in the process that's processing these events. So an example for that would be, let's say the user is searching for movies, and we want to create a session out of the search sessions and figure out how many such search sessions happen and what could we do better to make the user experience better. So in this scenario, we're trying to create custom windows out of other events, because you could press a key and each key becomes an event, and they could be delivered out of order because these are happening on a device, it's happening on a television at your house, and they get routed back to our backend, and it could be delivered out of order. Right? There's no guarantee of it being delivered in exact sequence as it happened. So you could have as S start event and E is the end event, and this could define a session. So this is the best case where you get them in order. There's another scenario where you could get the start event and you may not get the end event for a while, and your session may span for hours. And then you get an end event, right? And then you get another start event. So now we pick the start event, that's the earliest, and then the end event, and then now we've formed a session. So to do something like this, you have to retain those events in the state of the processor, and then you can do any aggregations, or you can emit results based on your window once you've identified the session window. Or you could decide that the end event didn't arrive in a certain timeout, and you could just drop the whole session, or park it somewhere else in a dead letter queue and come back to it later. So with stateful streaming application, there's local state. Now, when there's local state, how do you guarantee accuracy when there's fault and fault domains in your system? What if some parts of your job goes down, some containers go down? How do you recover, right? So this is where we could rely on checkpoints and save points. So there's a quick animation here that'll draw the difference between the two. So as the system's flowing through, you can configure regular checkpoints through the system. So what it does is, based on the duration you've set up, it takes regular snapshots of the data that are being accumulated, the states that's being accumulated. And it does deltas of it, so it only does incremental checkpoints. And then as a user, you can actually trigger explicit save points. So the difference between checkpoints and save points is the save point takes a complete global snapshot of that point in time. And it does it in a very safe way. That means it makes sure that nothing else is being processed while it took that save point. And if you recover from that save point, it'll start off where it left off. So let's say you're processing offset 100 from Kafka, and then you process the first 100 messages, and then your job went down, and you'd taken a save point before it. When you come back and start from that save point, it'll actually start from message 101, and then it'll start processing accurately from there. And with checkpoints, you're only taking incrementally, and those are useful when you have a partial failure of your stream processing job, because it could be running on multiple instances, and 2 of the instances could fail. The other 10 are running fine. And this helps you do partial recovery. And we leverage the functionality in Fling that supports distributed checkpoints and save pointing. So we have added some additional tooling in our pipeline. We don't have the UIs yet. We're working on it, so I don't have a demo for you on that. But what we do is, before we do a redeploy or a deployment, we automatically take a save point on Amazon S3. And we have the ability to automatically resume from the save point. When they say, I want to redeploy, they can pick a save point, and then we'll resume from that. And in addition to that, the checkpoints are automatically configured out of the box, so it'll automatically detect checkpoints. So if there's partial failure, it'll partially recover. So the user does not have to do anything special for checkpointing, and they don't have to do anything special for save pointing, except to choose which one they want to resume from. If they don't choose, the most recent one will automatically get selected for them. So some of the high-level features, just to summarize, we could work with stateless jobs, stateful jobs. We can do event enrichment. We can use reusable blocks. So what we saw earlier about the different sources and sink connectors in the Keystone Pipeline can be leveraged in here, so that you can just say, I want to write to Elasticsearch with this whip, and we'll figure out the configuration. We'll locate the servers. We'll do the batching in appropriate retries, and we'll send it to it. We'll generate the metrics. We'll do all of them for them. So they can just use this component and attach it to their job and just say .sync, and they can write the events there in the code that they're writing. So right now, our stateful jobs, we have that does hundreds of gigabytes of state. At any point in time, it's live. And we're working to support much larger state for some of the use cases that we have. So we're just getting started on the streaming jobs part of it. We want to do easy resource provisioning so that we can provide them with the right bootstrap set of machines to start off with. And we're trying to continually evolve this tooling as well as we go along. Our tooling is kind of generic enough that we're also looking at adding support for Spark streaming. We have a smaller use base of using that technology, but we can easily leverage the same tooling for Spark streaming as well. So what scale is all this running at? We've seen a significant increase since the last 3 years in the amount of events that are being produced into our system. So we process over 1.3 trillion events every day, 600 billion uniques to 1 trillion uniques, depending on the season. So we are hitting the peak season slowly, so we'll see a lot more events flowing through our system now. And about 2 petabytes comes in, and if you recall, we have a fan out depending on how many sinks the data is going to. And so we produce about 4.5 petabytes every single day. We peak to about 12 million events and 36 gigabytes a second. And all this is running on, when you saw the different paths, we looked at the streaming job that had 3. We have about close to 1,900 of those jobs actually running today. It runs on over 9,000 containers and on 3,000 M4 XLs. So this whole infrastructure is only the routing infrastructure. This is not the streaming jobs one. And this thing is fully managed, as I was saying. It's serverless for the users. So the question is, how do we do it? So we have 4 core pieces in our platform. One is the core messaging system, and we use leverage Kafka for it. And we have our stream processing layer that we looked at. And we have something called a Keystone management service that does the orchestration of this. It's the thing that's backing the UI, and it has some cool automations around it. And Keystone Pipeline kind of leverages all those 3 blocks, and it's built on top. And then the stream processing jobs gets used to it again. And we also have a development environment, a test environment, and a prod environment. And we have functionality to do granular shadowing. What I mean by that is you may have a small job or a small stream, and you have a new version of it. You want to try it before you deploy it. So we have functionality to kind of try that in production with a different stream, and you can route it to a different sink. And if you see everything's fine, then you can say, OK, now let me enable this for actual production. So back to the graphic, as promised. So the stuff that's not grayed out are the components of the streaming pipeline, the Keystone pipeline, and the streaming jobs. And we'll peel the layers one at a time of each of these components. So let's look at the producer library. So this is a Kafka client wrapper on the Kafka library, and we use 0.10 version of Kafka. What we automatically do when a user uses this library is we inject certain amount of metadata into it. Unique timestamp, unique ID, a timestamp, a host that's coming from an app. And this is really useful for us downstream to do some deduplication and identify where the data actually came from. And we also do transparent routing of producers. What I mean by that is if we add a new cluster tomorrow and we want that producer to route to it, the user does not have to make any changes. They don't have to redeploy. They don't have to change their app. We change a dynamic property, and we reset the connection to the Kafka cluster, and the producer starts producing to a different cluster. So it automatically happens, and the user is not involved in it. We can easily manage that. And I talked about our custom binary data wrapper that allows us to support multiple serialization formats, and also it allows us to add additional metadata that we can use within the system. And it has really tight integration into our Netflix ecosystem of metrics and discovery service and dynamic property services. So the boundary of the custom data wrapper is just within the pipeline. We don't expose it downstream unless the user explicitly selects to get it in the Chasqui format as we saw in the UI. Otherwise, it's bounded within our system boundaries. And when it lands at a certain sink, like Elasticsearch or Hive, it lands in a JSON format or another format that they've specified. So our goal is to keep the uptime really high because these libraries are being used in API servers and other end servers that are serving actual user traffic. So we don't want to impact those. So our approach is to drop a few events rather than actually impacting the application that we're running on. So that's why we run with ACK=1 in Kafka. We run with unclean leader election. We don't allow keyed messages into our fronting Kafka cluster. And we also have several retry mechanisms built in. And we do a round-robin write of events into Kafka, which allows us to make sure there's at least one partition available, even if there's an unclean leader election. And despite these discounts that we've done in the system, this is a little conservative, but we do upwards of 4 nines of reliability on our fronting Kafka clusters. So we have SLA of not losing more than 1% of data per stream every day. So it's a pretty high SLA, and this format has worked for us so far. So the next is the gateway proxy. This is just a REST or gRPC-based proxy that non-Java clients can use to send events into our system. Then it's the fronting Kafka clusters and the consumer Kafka clusters. And we have message sizes anywhere from a few kilobytes to up to 10 megabytes. And so that's one reason why we have to look at a custom solution rather than use something out of the box. Our Kafka clusters also get used for ad hoc messaging, not just for the analytics use case. And we also makes it easier for us to do enhancements. Like, for example, we added rack-aware deployment partition assignments to it as well. And we can make some other enhancements to it for integration into our ecosystem better, make it easier to deploy and make changes to it. But most of the time, all the stuff we do, we try to contribute it back to open source Kafka. The only con for this is it's not managed for us. We have to build and manage this service. So coming back to why we have the segregation between a fronting Kafka cluster and a consumer Kafka cluster, apart from the high availability, is also a way to scale. Because we have a very large fan out compared to the messages coming in. And to support that large fan out, we take a couple approaches. One is the hierarchical arrangement of clusters, so that we have one cluster that's producing, we take that and put it into another cluster, and then we can fan out from there. And there's I'll get to it, there's a limitation of the number of brokers we have in a cluster, so that's why we need this hierarchical nature, because our clusters cannot grow indefinitely in the number of brokers we have. So the alternative solution is just logically shard the topic across 2 clusters and then read from them. This is something we are actually working on right now as well. And there are some challenges around when it comes to key topics and being able to do failovers. But this really offers us functionality to do quick failovers if you wanted to. And the producers, if they use this library, the multi-consumer library that we're building, then it's transparent to them. So it allows us to do failover and fault tolerance really easily for our consumers. We do that today for our producers, and I'll go over that in a second, how we do that. But consumers, we don't have that functionality, so this would provide us that functionality. So I'll quickly run through these deployment strategies. And if you want to know a lot more, we have a presentation from my colleague at Kafka Summit this year, and you can look at all the details. But at the high level, we try to keep our cluster small, less than 200 brokers, and less than 10,000 partitions. We have a dedicated Zookeeper cluster for each cluster, so that any outages in one Zookeeper cluster does not take out our whole farm. We do rack-aware replica assignment so that it's zone-aware, and outages in one zone, we don't lose all the data. We keep 2 copies, and we do only unclean leader election on the fronting clusters. When it comes to the consumer Kafka clusters, we may relax that and have more copies, but as of this time, we don't. And we don't use any transactions yet. We use O10 version of the cluster. So we have over 36 clusters running in different regions. And we have over 4,000 brokers. And this runs on EC2. This does not run on containers. And we have over 700 different topics that we support on this. And it's highly available, and we use different retention time periods depending on which cluster and topic it is. And they range from 2 hours to 24 hours. So now looking at the streaming jobs, the router and the stream consumers, and let's see how that's getting built. Excuse me. So at the high level, the user creates the configuration in point and click. We launch the job using our deployment tooling called Spinnaker. It's the continuous delivery platform that we have. And once the user specifies declaratively the filters and projections, we package that configuration, and then we launch the job on our container runtime. And the image they provide us is immutable. We don't change the image. We just change the configuration that it gets deployed with, which overrides the configuration that's baked in. And it's, this platform's built on Flink 132. And each Flink router, as I was mentioning, becomes its own stream processing job. And the provisioning of these routers are based on incoming traffic. So we look at the incoming traffic based on the user estimate initially, or if it's a live stream, then we look at the past week's traffic every so often. And then based on the traffic, we either scale it up or scale it down. So the user does not have to worry about it. And we also have an override on it. For cases where we know that somebody's going to produce large streams and it's planned, we can scale it up ahead of time so that they don't see any latencies. And all the streaming jobs run on our container runtime environment. And we don't have any cross-region streaming jobs at this time. All of them are contained in each AWS region. So when it comes to the custom streaming jobs, we looked at the stateless and stateful examples. It's a similar flow. We leverage the similar tooling that we have. The difference is the user provides us the code rather than we providing the code. And the management of it is split. So they manage the business application side of issues and problems that they happen when it runs. We manage the infrastructure part of it. So if you peel the layers, and see what actually is being used. At the bottom, we have EC2 where it runs on. Then we have our container runtime system. And then the core of the framework code that we have is the stream processing platform that's based on Fling that has integrations into the Netflix ecosystem and build systems. And then on top of that, we have reusable components that they can include into their projects. And then on top of those two, we build the routers and the streaming jobs. And then we have the orthogonal functionality about monitoring, dashboards, development, and tooling that's leveraged across the stack. So digging in one more layer deeper, how does this actually get deployed and what's the architecture of Flink? Flink has a very similar architecture to Spark, if you're familiar with. It has a controller within a job called the job manager, and then it has a bunch of task managers, which are like the executors. And there's a leader. You can run it in a non-HA mode, then you only need one job manager, but we run it in an HA mode so that the remaining job manager can pick up if one fails, so the job's always up and running. And so the job manager is responsible for creating the job graph, taking the job graph, and getting it executed, coordinating the checkpoints, triggering the save points. So it helps kind of coordinate those activities. But it's pretty light on resource usage. We run it on just a 2 CPU container, and it runs fine. And if you look at what's happening inside the task managers, Flink likes to split it up into what they call slots. And each slot can have operators chain. So for example, if you have a filter and a map, those don't get scheduled on different machines. They get collapsed and run on one box in one process and one thread. So that way you get a lot of efficiencies out of the box there. So talking about save points and checkpoints, as I was talking about it, the job manager actually triggers it, but the checkpoints are actually taken directly by the task manager. So they're distributed in a fashion. So the snapshots are distributed. They're not all funneling back to the job manager and saving it somewhere. It's just a trigger, and each task manager will actually save it independently onto the backend store. So this is from the Flink docs, and it talks about how the checkpointing mechanism works. It's very much similar to like a two-phase commit where it waits for all the acts for the checkpoints. and it waits for everybody to having flushed out those checkpoints, and then it says, okay, now the checkpoint is complete. So the checkpoints are taken often. We have jobs that are set up to 15 seconds. Every 15 seconds, we take a checkpoint. So we only have to do 15 seconds worth of work if there's a failure and we recover from it. And some of the things that get saved in state is like Kafka offset is one of them, in addition to the state that you may be building. So let's say a cluster in your job, one of the containers failed, right? And when the container fails, we'd already been saving state on a regular basis. And now our container runtime automatically replaces that container. The container joins the job quorum, reports to the job manager, so it's back in the job. And now whatever failed, whatever operations failed on it, gets rescheduled on it. And before it gets rescheduled, the state got restored. So it can resume from where it left off. Now you might reprocess a few events again, and if your sink is not idempotent, then you'll end up creating duplicates. But this is in at least one system. So if you want an exactly one system, then you'll have to have end-to-end control over your source and sink. Either it has to be idempotent or it needs to support transactions. So let's dig a little bit into the management service and how it's being built. So this is the current architecture, and I'll talk about what we are moving to. So right now what happens is when you look at the provisioning of the streams in the UI, or we're launching a new streaming job, we need to actually take those actions somewhere. So this infrastructure creates what we call as joblets to create a topic, to create appropriate metrics, to launch a streaming job on a container system. And these joblets are chainable, and these joblets are reusable because each one does one thing accurately. And once that graph is kind of figured out, it gets scheduled on the workers, and it gets through Amazon SQS, so it's fault tolerant. And so currently, that's how it works. We are moving to a little more declarative approach, where what we want to do is we want to take a look at the current state of the system, and we want to take a look at what our goal state is and where we want the system to move to. So for example, you could have a Kafka topic that's 10 partitions and doing 10 megabytes a second. And a user says, I actually want my stream to be 30 megabytes a second. And for that stream, the user does not know how many partitions. They just say, this is my bandwidth. So from that, we figure out, okay, this actually needs another 20 partitions. And then we reconcile that difference, saying the current state is 10, we actually need 20. How do we actually drive the system towards that end state? And so we look at the cache of the goal state and the current state, we compare it, and the reconciler kind of runs its magic on it, and then figures out what needs to be done, and then it schedules the job on the job runner. And the job runner does the same thing like we saw in the previous picture, where it sends these jobs to a runner framework and it executes it on our behalf. So the benefit of this is even if there are failures across the system, we'll discover the current state and that it's not at the state that we want it to be, and we can always reconcile easily. Because in a distributed system, you'll always have failures when you're trying to access multiple systems. And this is actually managing across several different systems within Netflix. Kafka, the stream processing engine, metric system, the continuous delivery system, the container runtime system. So when it's working across all this, you have to make sure you have a kind of a good reconciliation architecture to deal with this. So this is how the new kind of architecture looks like. Every major component, one that's managing Kafka, one that's managing stream processing, gets its own reconciliation framework. And on top of that, we have another reconciliation framework that kind of ties all this together. So it's like more like a composite pattern where we are taking the blocks and using the same thing at different levels, but making it really more declarative. So this way, when we start building new flows, we don't have to hand code everything. We just specify the current and goal state, and then we convert this into like a search space problem and use A-star algorithm to kind of search through the space and figure out what we need to run and how we need to run. So it gives us this dynamic composability of stuff that we want to do management-wise. And it allows a lot more flexibility in what we want to do and less time in coding every single pathway through the system. So The unique features are this system allows us to add locks and semaphores on critical resources that we have. So for example, we can only launch containers at a certain rate because of certain limitations. And this allows us to set those limits. And so these are some of the reasons why we were not able to use AWS step functions in SWF, because we needed these functionality for our framework to provide us the functionality that we need. So towards the last section, how do we actually operate such a large system? So as I was saying, we scale operations using systems and not humans. That's our motto. So we try to do as much automation as we can. So everything that I showed you today, we actually build it and we run it. So we don't have a separate ops team. We don't have a separate QA team. There's no separate dev team. It's just all one team. We're about 10 developers and 1 UI engineer in total that's shared. And so we are the folks who actually build this functionality. And we rely heavily on collecting metrics, doing the appropriate monitoring, automated paging, alerting, and remediation too at times where we can terminate certain Kafka brokers or restart certain jobs automatically based on alerts that we have. And we heavily rely on other Netflix system as well. We have a separate metric system called Atlas that manages and dashboards all our metrics. We have a separate dynamic configuration system that's that we leverage heavily. And we also have built-in automation systems that allow us to write Python script to automate some aspects of it. And that's closely tied into our alert generation system. There's also a lot of automation within the Keystone management functionality that I showed you as well. We have a very easy way to look at the alerts that are fired or configured. And here's another view of the alerts that are currently fired, so we can quickly take a look at what's happening to our systems. And operating our gateway is pretty simple. It's a stateless service. We use elastic load balancing and auto-scaling to scale up and scale down that service. The event producer-related metrics and monitoring. So here is a dashboard that shows what we track across the system, like how many events are produced, what's the drop rate, and are there any applications that are falling below the SLA that we have specified, or are there any topics that are falling below the SLA at the high level? So when it comes to Kafka clusters, we have developed tooling to do automatic Kafka failover. So it's a one-button failover and reset when we are done with the failover, and this is how it works. Let's say we have a happy path Kafka cluster, we are routing events, and something bad happens to that cluster. We leave the Flink router running in case we can still extract events and route it back to the event. We actually create a brand new Kafka cluster of a smaller capacity. Same number of nodes, but each node is a smaller node for cost reasons. We copy all the metadata, we recreate all the topics, and then we change the producer through dynamic properties to automatically start routing to the new Kafka cluster. We launch another router job, so it starts routing. So this gives us time to recover and fix the old cluster without having to drop any data for our customers. And once the cluster is fixed, we point the producer back. We finish draining all the events from the failback cluster, and then we decommission the failed over cluster and the routing job. And then with the click of a button, we are back to steady state again. So for the Kafka consumer clusters, currently we don't have this kind of automated failover because we need the consumers to move over to a multi-consumer library approach. And we use this automation also as our Kafka Kong. We do this routinely. We actually intentionally fail over on a real-life traffic to make sure actually this stuff works when we really need it. So we do it very often, and it's planned. So we monitor a broker health in terms of networking, broker fetch latencies, replication latencies, and when we identify an outlier, we have some automation that will automatically terminate a broker. And we only terminate one in a certain period of time, so we don't have the risk of losing data if we accidentally terminated both the copies. We scale up by adding partitions, and we add partitions by spreading them evenly across brokers. And that's how we do our partition assignment. We scale down or up by using the same failover functionality that I showed you. We just start up a brand new cluster, we just route the events to it, and we just tear down the old one. And that's how we do our upgrades as well. So we have zero downtime upgrades and scale ups and scale downs. And we leverage the same functionality, the failover functionality for it. So for the stream processing jobs, as we talked about, we have checkpoints, save points, container replacements. We have built-in retries into the framework and also isolation between the different streams. We have router deployment options where we can do automatic partial recovery. So there's a feature in Fling called fine-grained recovery. So it analyzes your job graph, and if you have parallel streams that are not dependent on each other, think about it as a digraph, and if you don't have any dependencies and if there's a path to it, it'll continue running that path, and the ones that it failed, it'll recover them. So that way, you're not lagging behind and not processing anything at all. You're actually processing that stuff. So this is something we found based on our testing, and it's something we helped add into the Flink runtime, because it's really useful for our routing jobs. And of course, not everything can be automated. There are always some cases where we need manual intervention, and we have good runbooks for that. And this is one scenario where the UI pops up and saying it needs manual intervention, and the user can, or somebody who's on call can follow up on it. So we do a lot of capacity planning, and we do this ahead of time looking at the traffic that's flowing through the system. And sometimes we manually increase it as well in anticipation of increased traffic. Like, for example, right now we're getting into the holiday season. So this is a place where we can actually do an override and increase the capacity in addition to what's automatically determined based on the input traffic. Because we could say this traffic's going to increase 2x, but that traffic's not actually flowing in, so there's no way to determine that. And so this is where we can override it. And we can do bulk updates or upgrades of routers across our whole ecosystem, so that deployment framework makes it very easy. So this is, again, the message flow. We look at application metrics heavily for operations. This is the filtering metrics, which tells us what's getting filtered and if there are any drop messages because of filtering and errors. And these are the Kafka offset metrics, like how many records are coming in, what Kafka offsets per partition we are doing. So this allows us to look at clustering. If something's way off from the clustering, we know it's an outlier and makes it easy for us to identify them. And then we have the same mechanics for JVM metrics as well, where we try to see the clustering and see if there are any outliers. And so this direct buffer and the usual JVM metrics that we measure. There are a lot more metrics that we measure, but it's hard to kind of list all of them here. So this is a view of the alerting UI again. So the streaming jobs that the user developed, this is an interesting mix because there are gray areas where it may be an application issue or it may be a platform issue. So that's something we are kind of working on with our customers to see how much of it they can address the pages versus us, but it's kind of a split right now. And we have automated paging systems at pages to do it. And our platform customers also follow the same model. If they build the job, they're responsible for running and operating it, unless it's a problem with the infrastructure that we've built. And then they can reach out to us and escalate it to us. So these are some of the metrics, like how many, and this is an example application that we wrote to quickly get these data points. But it talks about how many enrichments were happening, how many counts they did. So this is more of an application level metrics that they added. There's some system level metrics. So the road ahead for us is to get to a more true auto scaling. We don't have true auto scaling right now. And to have better provisioning for streaming jobs, because it's difficult to know what code user is written and what the performance profile is. So we want to build some tooling to gauge the performance profile and then work based on that. So if you want to learn more, there are a bunch of related presentations that we've had in the past, and then you can hit them up and take a look at it. Thank you for coming.